Okay, I'm going to run through this problem. This is finding the area underneath polar curves or between polar curves. This is out of the Briggs Calculus book, chapter 12. And in my math lab, this is actually problem. I found this problem. It's number 51, chapter 12.3.51. So the idea here is that we have a rose with various amounts of petals that has a certain orientation. We'll figure that out. And a circle that has a radius of this. So how do we figure out what our rose looks like? It's good to know what it looks like visually so that we can determine symmetry. We might have symmetry across the y-axis, in which case we could do maybe a 0 to pi calculation and double that, or depending on what we want. Or we might not have symmetry across the y-axis. We might have other kinds of symmetry. Origin symmetry is nice as well. So let's figure out what we have here. Well, as you know, cosine polar graphs, roses and things, will have a petal on the x-axis, whereas this one, sine, will not. The other thing to keep in mind is the angle has a 2 theta, and when you have an even number, even coefficient, you'll have double that many petals. When you have an odd, you'll have just that many petals. So 3 theta would have 3 petals. And we do some kind of symmetry, first, third, and maybe the y-axis, whereas this has actually 4 petals. So this is going to be right in the middle of each quadrant would be how this works. So, the axes of each of these petals would have a reference angle of 45 degrees in each quadrant. So pi over 4, that's not going to be needed, but keep that in mind as a reference. And actually, if we wanted to know how far out this would go, well, we would reach our maximum value r. R is the distance from the origin to the graph at any given point. Our maximum value would be when sine is 1, and sine reaches 1 when the angle is pi over 2. Therefore, theta would need to be pi over 4, doubled into pi over 2. So this is actually where it reaches its maximum. 1 times 12 is 12, so this would be r equals 12 away from the center. Okay, some maybe more information than we need, but just getting used to what our graph looks like. Now our circle, of course, is going to, well, that's actually good information because this goes 12. Does our circle completely expand outwards from the rows, or is it smaller than the rows? Is it equal to? These are all important pieces of information. Well, 6 times square root of 2 is around 6 times 1.4, so that's 8 point something, whatever. That's less than 12. So we know that the circle is smaller than the extent of our petals. So this is good information. It's going to cross twice in each quadrant. And we also notice that we have all kinds of symmetry. And so now what area are we looking for? We could be looking for all kinds of areas, so we have to read the problem. Inside the rows and inside the circle. So it's this area here within the rows and the circle. And so we'll have to be very careful on how we integrate this. But one thing we can see from this rough sketch is that when we could calculate the area in the first quadrant and quadruple that. So 4 times the area in the first quadrant. And so now let's just look at the first quadrant. Okay. Circle there. Now, the other thing we need to know is the polar degrees, the polar angles where these graphs cross. How do we do that? Set the graphs equal to each other. When the radius, the distance from the center to that graph are equal, that's when the graphs will cross. So we set 12 sine 2 theta equal to 6 square root of 2 and solve for theta. So divide by 12 square root of 2 over 2. Where is sine equal to positive square root of 2 over 2? Notice that's a positive. This could have very easily, they could have given us maybe a negative, I don't know. So this is positive square root of 2 over 2. Sine is positive, if you remember from trig, in the first and second quadrant. All students take calculus, all positive in the first, sine positive in the second. So we have first and second quadrant, and the reference angle for pi over 2 over 2 for sine is 45 degrees, or pi over 4. So this angle must equal pi over 4. Sine of pi over 4 is equal to square root of 2 over 2. Or we said second quadrant as well. So first quadrant, second quadrant. Not 5 pi over 4, that's negative square root of 2 over 2. Or 7 pi over 4, which is negative square root of 2 over 2. So these are the two angles. So 2 theta equals pi over 4. And 2 theta equals 3 pi over 4. So this actually means that theta equals pi over 8 divided by 2, 3 pi over 8. So here is the angle pi over 8, 3 pi over 8, and actually draw a line from the origin. It's supposed to be a straight line. There's a reason I'm doing this. And I wanted to illustrate that the area within the circle between pi over 8 and 3 pi over 8 is a wedge that doesn't include some of the area that we are looking for. And that's very important to keep in mind. It might be tempting to do the area of the circle, since the area of the petal is just extra stuff on the outside, and just do the area of the circle between pi over 8 and 3 pi over 8, but you'll be missing out on some little slivers here. You won't be including a little bit of area in these slivers, and we need to account for those slivers. And so if we do the area of the circle between pi over 8 and 3 pi over 8, and we multiply that by 4 for the other quadrants, we'll have most of the area that we need, but we'll be missing those slivers. So we need 4 times the area of the circle. Remember, area of a polar graph, area equals 1/2 the integral of f theta squared d theta. And so f of theta being r, this doesn't have a theta, it's a constant value. For all thetas, it's 6 square root of 2, but this is a function of theta. So our area of our circle, the wedge, is the integral from pi over 8 to 3 pi over 8, 1/2 function of theta, or r, squared d theta, which is just a constant value. So you can make this a 36 times 2 divided by 2, pull that all out, you'll just have a d theta integrates to theta. However, we need to quadruple that. Okay, now let's just cut that off there. And now separately, let's do these little slivers. How many slivers do we need? Well, we can do the petal from 0 up to pi over 8. If we integrate the petal from 0 to pi over 8, we will have our sliver that we need. And then we could do one for here, 3 pi over 8 to pi over 2. However, using symmetry, we do know that these slivers are equal in area. If you're not sure about that, just do each one separately. That's perfectly fine. But these are equal in area. So actually, how many slivers do we have? 2 in the first quadrant, 2 in the second, 2 in the third, 2 in the fourth. That's 8 slivers. So we need 8 slivers, and the area of each sliver is the integral, 1/2 times the integral of the function of the petal of the rose squared d theta. And so that is how we will set up the integrals for the areas. Right now, and by the time you reach Calc 2, you usually can use a function, integration function on your calculator, but perhaps you need to show that you know how to calculate this as well. This will involve a trig identity, square root of, or the integral of sine squared. You can use the identity, flip this paper over, write out the identity, sine let's say sine theta squared theta is going to be 1/2 1 minus cosine of 2 theta, which doesn't have a squared, but it doubles the angle. Therefore, sine of 2 theta squared is going to, this is the one we'll need. I'm modifying this to fit our need. It's 1 minus cosine of 4 theta. So this is the substitution that we'll need to make. And so just maybe do that integration real quick. Let's just see what happens here. Let's pull out all these constants. 12 squared is 144 times 4. So let's do that. And times the integral of sine squared 2 theta d theta. But instead of sine squared 2 theta d theta, we're going to put in 1/2 and 0 to pi over 8. And remember that first integral was just, what did I say, 2 times 1/2 goes away, 36 times 4. 2 times 1/2, yep, 36 times 4, okay. Integral from pi over 8 to 3 pi over 8, which is just theta from 3 pi over 8. Is that 120, 124, 144, and 288. And then integrating that, we'll get theta minus 1/4 sine 4 theta. That's a theta. Let's see. The derivative of sine is negative sine is a negative cosine, so the integral is, yep. So, and so when we plug in 0, these thetas go to 0, so that's nice. So we can just worry about the upper bound, where we get pi over 8 minus pi over 8 times 4 is pi over 2. Sine of pi over 2 is 30. Sine of pi over 2 is 1. So this is 1/4. 288 plus 3 pi over 8 minus 1 pi over 8 is 2 pi over 8, pi over 4. What is that, 72, 36. So we get 36 pi plus, and then this is going to be 2 pi over 8, pi minus 2 over 8. I don't want to do this wrong, divided by 8. 36. Got somebody chewing on the pencil. 36. Gosh. Come here. Sorry about that. What would it do? Pi minus 2. Bring the 8 out, pi minus 2. So 36 plus 36 minus 72. So I think it's 72 pi minus 72. So there we go. That would be the area in all 4 quadrants of these slivers plus the wedge plus the sliver. Okay, I think we're good. Thank you.